We would naturally have preferred to welcome you to our school and to meet in real life. But unfortunately, real life does not permit. All the same, it's a great honor for our students to take part of your insights, albeit in Zoom and not the same room. Some might say that it is a big leap from studies at upper secondary level to researching at a level which earns you the Nobel Prize. And that's of course true, but there is also an important link between the two. In 2015, the Swedish researcher Thomas Lindahl was awarded the Nobel Prize for Chemistry. In his speech at the Nobel banquet, he talked about his teacher in upper secondary school in Stockholm. Their great knowledge, their support, and their ability to create an interest were crucial to Professor Lindahl's possibilities to succeed in his further studies at university and in his research. Therefore, we are happy today to get a glimpse of research at the highest level and hope that our students will be encouraged to set goals and get motivation for further science studies. Allow me to introduce Professor Mats Larsson, member of the Royal Swedish Academy of Science.
Thank you. And I will now try to share the screen. Let me see. Yes. I think I now, just for a moment, switch to Swedish, because here you see the motivations in Swedish for this year's Nobel Prize, the citations. Och den lyder på följande sätt då, att ena hälften av priset går alltså till Roger Penrose, University of Oxford i Storbritannien. Och motiveringen lyder: för upptäckten att svarta hål är en robust förutsägelse av den allmänna relativitetsteorin. Och med andra hälften gemensamt till Reinhard Genzel, Max Planck-institutet i Garching, Tyskland, och Andrea Ghez, University of California, Los Angeles, USA. Och där lyder motiveringen: för upptäckten av ett supermassivt objekt i Vintergatans centrum. So this is the motivation in Swedish, and then of course this is always translated, but I thought it could be interesting for you to actually hear it in your native language. You often hear this in English, but this is how it was motivated in Swedish. So, and I should also mention, unless maybe you know this, but the maximum number of Nobel laureates in a given subject a given year is 3. So here the Nobel Committee has actually used the full bandwidth of how many laureates can be awarded a given year. And of course, the common theme here of this year's Nobel Prize is the black holes. So I think I stop here and leave the word to Professor Genzel, who is so far the only laureate who has been able to connect. And the order was that we should have started with Professor Penrose, but we start with Professor Genzel and hope that, that we can have some of the other laureates also connecting within shortly. So I now, let's see, I should stop sharing like this, and then please.
Okay, Professor Larsson and Ms. Bejmar and students of the Nacka Gymnasium, it's a great pleasure to speak to you. Would have been, of course, much more pleased to be where you are. We've been relatively free, like I believe you in Sweden, but about to enter here in Germany into a hard lockdown. So it's gonna, for the next day, is gonna get pretty difficult. Well, now, given that the others are missing, I'll improvise a little bit. in order to get the full story to you. So I've called this the 40-year journey. Really, it is a 100-year journey, because the theory of general relativity, which started this all, was first published in fall of 1915. And already 1 year later, the first solution for a spherically symmetric, non-rotating space-time was found. And that had a very great surprise in it, which is that if you make objects of a certain mass more compact, then of course the gravity on the surface of the object increases. So if you in your mind take a rocket at the surface of the Earth, well, then you need a certain speed to get away from the Earth into space. Now, if you make this Earth smaller and smaller, then Newton's theory, or Kepler, would tell you that if the Earth is in your mind 1 centimeter across, then the rocket would have to move at speed of light. But we know experimentally that the speed of light is, so to speak, the fastest communication speed. So obviously, if gravity is very, very strong, then even light cannot escape. So that's the basic idea, or one of the basic ideas, which came out of general relativity already in Karl Schwarzschild's solution in 1916. And of course, lots of theoretical work followed, and I'll leave it to Roger to tell you more about this. The next step really happened 50 years later. And that is the discovery of objects which might be these black holes where light cannot escape. Before that time, the idea of a black hole was a purely theoretical concept. But then in the 60s, remarkably in the 60s, 3 things happened. Number one, the X-ray astronomers discovered compact, highly X-ray bright stellar objects in binaries, which we now believe are stellar black holes. So these are objects which have a mass of a few tens or 10 solar masses. At the same time, the radio astronomers started looking at the skies, and they discovered new sources. And then they told the optical astronomers, why don't you look at these sources and tell us what they are? And so one of them, which you see here, which was the first one, 3C273 from the Cambridge Radio Astronomy Group, was then looked at with the Palomar telescope by Martin Schmidt. And he found that in the optical image, which pretty much looks like a star, a faint star, there were spectral lines, which all were very well known, but all redshifted by about 16% relative to the laboratory. Now, if you believe that this is due to the expansion of the universe, well, then this little star which you see there must be 2.4 billion light years away. So if you then convert the amount of energy which we see in the optical into a luminosity, then this little star has 1,000 times the luminosity of the Milky Way. So this discovery in 1963 really started, in a way, the thinking, and then, of course, also the observations, which have kept astronomers busy for the next 50 years. And it's really a very active field. So why do black holes come in here? Well, if you think that this little object there with 1,000 solar luminosities is actually very much like a Milky Way with lots of stars in there, very compact, it's very difficult with the efficiency of fusion from hydrogen to helium to illuminate such a quasar for any length of time. That became very clear very quickly in the years following Schmidt's discovery. And so a number of theoreticians started to think about, well, would there be other possibilities to generate more efficiently energy? And surprisingly, paradoxically, black holes can do that. So whilst there is for each black hole a characteristic radius, which you call the event horizon. From within, you cannot escape. You cannot send light out. If you're outside of the event horizon, in fact, you can. And so if you have a lot of material falling into such a black hole, that's depicted on the right side there as a disk, because if you have angular momentum, likely configuration is a disk-like configuration, which then through friction, magnetic, we believe, friction, slowly spirals inward. And as it approaches the central region where the event horizon is, it gets very hot, such that you can release enormous amount of energy. In fact, in the so-called extreme rotating black holes, which Roy Kerr discovered theoretically in the 1960s, along with Roger Penrose, thinking about these black holes, well, then you can actually release up to about 40% of mc squared before the material disappears behind the horizon. So that compares to fusion, which is about 0.5%. So that's 100 times more efficient. So remarkable. These black holes, in theory at least, can be much more efficient radiators than stars, and therefore they might account for these spectacular objects called quasars. But how would you prove that? I mean, that's sort of a proposal. Of course, there are spectacular things you can observe, like so-called radio jets, which are very collimated streams of hot plasma going away from these central regions. There's also X-ray emission, sometimes even gamma ray emission. But that's not a proof that this must be a black hole. So how would you prove it? Well, you would have to sense the gravitation which such an object, the speculated black hole there, would act on the environment, stars, gas, and anything else. But that's too far away. These objects are too far away, even nowadays, to make such measurements. So Lindenbell and Rees, two very famous Cambridge theorists, proposed the following. They said, well, if these black holes are common, in the extreme case, every galaxy has a black hole. And indeed, that's what we now believe. Then you might actually look much closer than the quasars and see through dynamical measurements whether they might have such black holes. And Lindenbell and Rees in a 1971 paper then said, well, in fact, might be that the closest of all galactic nuclei, which is our galactic center, which is, several 10,000 times closer than these quasars, only 26,000 light years away. If there's a black hole there, well, maybe you could see it by its action on the environment. So that's how the whole story got started. And in the end 1970s, the observations really started in the galactic center and then also other nearby galaxies. Now let's fly into the galactic center from our vantage point in the outer parts of the Milky Way. And you immediately see one problem as you approach the central regions. There's these dark patches, and that's dust, interstellar dust, which in fact obscures the center of our Milky Way, which you're now beginning to see there by 12 orders of magnitude. So you cannot actually, in the visible, look at the galactic center. You have to go to the infrared, longer wavelength, radio, or shorter wavelengths, X-rays. Nowadays, of course, we have exquisite detectors for these long and short wavelengths and can really look into these regions. And in the galactic center, what you find is in blue there, a very dense star cluster in the center, about 1 million times denser than our environment here. So that at night in the galactic center, it would be bright. And then in addition to the stars, you also see gas, which is here in red, which is ionized gas, and green, which is neutral gas. Big gas clouds swirling around. And at the center, and that you see on the left side of this radio emitting hot gas is a very compact radio source, which was discovered in the early 70s and is now called Sagittarius A star. We know that this object has a radio size in millimeter waves, which is only a few tens of microarc seconds. That's about the size of a euro coin on the moon. So could that be a black hole? How would you prove that? Now, in California at the time, a very famous physicist, Charlie Towns, who in fact got a Nobel Prize for the invention of the maser and the laser in 1964, had later on moved to California and started doing astronomy remarkably. And he built equipment with his students, and I then joined, in fact, at that time as a postdoc initially, later on as a faculty member. So we built equipment in the infrared where you can peek into this region and look at the motions, the Doppler motions of the gas clouds. And you see this depicted there with these white arrows. And we found that the green gas, for instance, was in a pretty much a rotation, just a little edge on, whilst the closer in ionized gas was basically falling into the central region. And so from the magnitude of the motions, Towns and his collaborators could find that there must be a mass of several million solar masses concentrated in the central light year or so. That cannot be explained by stars. So that was, so to speak, the first moment. In fact, we wrote a paper down there, you see Crawford et al. In 85, a Nature paper, where we basically said, well, we've seen these motions of the gas, and that is very likely a massive black hole. So there you go. That's the proposal which was made by Lyndon Bell and Rees. But is that really true? Could there not be other configurations? And so this is where, if you like, my personal 40-year journey just got started when we already had a result, because in order to prove that this thing, this few million solar mass object really is a black hole, you have to go very, very close, eventually as close as the event horizon. And that requires very, very sophisticated technology, and that took time. And it took 40 years, in fact, and is still not finished. So in the 1990s, two groups, one were working with the European Southern Observatory, that was me, who had, with my group, in the meantime, moved to Germany at the Max Planck Institute for Extraterrestrial Physics. And then another group at the University of California, Los Angeles, around Eric Becklin and Andrea Ghez, started building equipment for big optical telescopes and equipped them over time with ever more sophisticated infrared cameras, imaging spectrometers. Nowadays, in fact, illuminating the skies with lasers in order to eliminate the effect of the disturbances in the Earth's atmospheres and make, diffraction limited, very sharp imagery of stars in the galactic center. So that took this whole story to get to this technology. It took about a decade, within which, however, we did have progress. We saw motions of stars, very fast motions of stars, and the evidence that there might be a black hole was getting better. But was it good enough? Well, it took about a decade until we had given to us by nature a very unexpected star, which came now as close as the solar system scales, about 4 times the Neptune orbital radius, about 15, 17 light hours. So as you see, it's a very elliptical orbit, and at the closest distance, where it's 17 light hours from the radio source J star, it moves with about 8,000 kilometers per second. So that's pretty damn fast, more than 100 times faster than the Earth around the sun. And if you now measure from that, calculate with Newton what mass there might be within that orbit, you get the same few million solar masses, which we had already with the gas, but now within scales of the solar system. So this evidence, which became ever better and we had more stars over time, became ever more precise in terms of telling us that the mass, the million solar mass object, really very, very likely was a massive black hole beyond any reasonable doubt, as long as general relativity holds in this regime, which of course we can't know. That's part of physics. We need to test that. We need to ask the question, can we actually, on these scales, test general relativity? So by 2002, when this very closest approach had happened, both groups then knew the star would come back in 16 years with this elliptical orbit. So by 2018, star would be back. And maybe by that time, if we had good enough instruments, we could see the effects of general relativity. What we did was to exploit the fact that the site of the European Southern Observatory on Paranal in Chile has 4 8-meter telescopes. So we've been measuring so far with one of them. But then we built over 10 years an instrument which would combine the light of all the 4-meter telescopes, for all the 4 8-meter telescopes, thereby constructing what we call in radio astronomy an interferometer. And an interferometer has a resolution which is dictated by the longest separation between the telescopes, in this case about 130 meters. So that's another factor of about 20 over an 8-meter telescope. And now our resolution, our astrometric precision is 20 microarc seconds. That's a Eurocent on the moon, and only about 2 times the event horizon size of a massive black hole. So when the star came back in 2018, we could really precisely monitoring its orbit from day to day. Here you see it in the month around the Perry approach in May 18 and 19, 2018. And our colleagues at the Keck telescope did the same, and we both were making very precise measurements of that star. And indeed, with that data up to the point we now have, we could see several effects which are due to general relativity. One is the so-called gravitational redshift. See, the photons, as they come from the star to us, have to climb out of the potential, the gravitational potential of the black hole. And that results in a redshift of all the radiation of about 3 × 10⁻⁴. That's a small amount, but we can measure that. And both groups did. The second effect general relativity predicts is that when you have a star, or in this case a black hole, and you have an orbital second object, and if there's nothing around other than these two, then Newton's theory tells you that the object should run around in this ellipse, which is constant in space. Not so in general relativity. There is a precession called a Schwarzschild precession. Indeed, we've seen that now as well. There's a third effect due to the spin of the black hole. That makes a precession along the rotation axis of the black hole. That we have not seen yet because we need a star which is closer. And of course, we would like to do that. Finally, there's an effect due to hot gas right around the black hole. So the black hole itself actually is lit up every day for a few hours. And we believe that's due to hot gas right around the event horizon. And we see that move. And we see it move at about 1/3 of the speed of light. So at this point, experimentally, we've moved, we've shown that the few million solar mass object which Charlie Townes had found in the 1970s is actually concentrated on a scale of only a few times the event horizon size of such a black hole. So that's very good proof that this object must be a black hole. Now you could say, all right, are we done? Should we pack it in? Now the answer is no, because we really need to show what's known the no-hair theorem. It's a remarkable thing which Schwarzschild, Penrose, and Kerr found, that there are only three quantities really you need to describe a black hole. Its mass, its spin or rotation, and then finally whether or not it has an electrical charge. Let's forget about that last thing. So really only two numbers, and therefore a black hole is a very simple thing. We say it has no hair. I mean, there's no mountains, no structure which you would have to know about. It's just a very simple object. And so, in fact, that can be proven by showing that the higher order moments of this object all can be expressed by the mass and the spin. So that's the very famous no-hair theorem. We haven't proven that yet. Now, there's another way of going at objects like this, for which a Nobel Prize was given 3 years ago, and that's gravitational wave radiation. In fact, for stellar black holes, the in-spiral of stellar black holes has been seen with LIGO. And also our colleagues in gravitational wave astronomy also want to do the same thing. And then finally, the millimeter astronomy community wants to prove that photons indeed run around in curved space-time and thereby cast a shadow of the black hole. So there's three techniques all coming together remarkably, I would have to say, about 100 years after the theory, which is now leading to ever better evidence that these black holes exist. Finally, of course, you might ask, so what good are they for? Why are they there? Do they serve any purpose in the universe? And in fact, what we've learned from many, many measurements in the last 20 years is that massive black holes indeed had a very important effect on the evolution of Milky Ways, especially early on when the Milky Ways were forming. So in a way, this story, this 40-year or 100-year story, has several aspects. One of physics, and we're not done yet. There may be the culminating experiment will be an in-spiral of a stellar black hole into a massive black hole seen with spaceborne gravitational wave techniques. And in astronomy, where we've learned that these massive black holes really are, very important for the evolution of galaxies. So it's a very active field, one which attracts a lot of interest amongst the physics and astronomy communities. I've had recently a look at the number of papers coming out with on this subject, and it's increasing exponentially, but as fast as the COVID virus. I mean, so it's clearly a very, very interesting and exciting subject. Thank you.
Thank you, Professor Genzel, and we will have questions later on. I now see that both Professor Penrose and Professor Ghez has connected. Is that correct?
Yeah.
Okay. Are you ready to give your presentation?
I am. I'm ready to go.
Okay, excellent. The floor is yours.
Okay, excellent. All right. So I recognize you've just heard the lovely talk by
Andrea. Sorry, Professor Ghez, we can't see you. There is no video. No.
Good morning. Oh, well, sorry. Good evening for you. Good morning for me. I realize what I just said was I realize you've just heard this lovely talk by my colleague, Professor Reinhard Genzel. So you're going to hear a second version on work that's done by a parallel group. So I guess my job is to keep you entertained, having to listen to these talks back to back. What I'd like to do next is to actually show my slides. I'm showing the wrong slide here, right? So share screen. So hopefully you can now see my screen. So the work that I'm going to share with you is the work that we've been doing at Keck Observatory for the last 25 years. When this project first started, when I started my faculty job at UCLA. So as I assume you're aware, when professors have roughly 6 years to prove that they have the ability to do interesting research, and then the university decides whether or not you get to keep your job. So for me, initially, this project was really about how can I define an interesting project through which I can get tenure. I had no idea how interesting this project would become. And in fact, I think this is true for both groups, that we started off with much more simplistic ideas, and then the technology just really took over. So this is really a story of technology-driven discovery. And to me, it's the kind of research that is the most interesting, where the technology opens up the path forward in ways that you couldn't have imagined at the beginning of the project. Now, the question I always like to start these talks with is, how do you observe something you can't see? Because this is such a fundamental question if you're trying to find and study black holes. So the question I started off with is there a supermassive black hole at the center of the galaxy? And underneath that, fundamentally, is the question of, do supermassive black holes exist? Black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light, so you can't see them directly. And they're really fascinating to study because they point the path forward to understanding more deeply fundamental physics. Today, we actually don't have the full description, the ability to fully describe what a black hole is. They effectively represent the breakdown in our understanding of how to make general relativity, which is the study of things that are very massive, have lots of gravity, work together with things that are very small, quantum mechanics, sorry. And so black holes are both. They have both lots of gravity and they're infinitesimally small. So we really do need to figure out how to make these two fields work together. And I think that's part of what drives researchers towards black holes, because they represent a path forward to a deeper understanding of physics. Okay, so while these objects are infinitesimally small, there is a size that we can associate with these objects, the Schwarzschild radius, named after Schwarzschild, who recognized the concept of this abstract size. So it's not a physical size, but it's an important conceptual point associated with a black hole. So the Schwarzschild radius is the radius at which if you compress an object to, or some mass to its Schwarzschild radius, and every mass has a Schwarzschild radius associated with it, gravity overcomes all other known forces, and the object becomes the infinitesimally small object known as a black hole. It's also the point at which light can't escape from the object. So it's actually the last point at which information can be carried, transported from the vicinity of a black hole to us. So in effect, it's the last point at which we can gain information from this object. But from the point of view of this talk, in terms of the proof of the black hole, the Schwarzschild radius is important because you want to show that there's some amount of mass inside a small region. Ideally, although we've gotten closer than anybody has, but we haven't quite gotten there. So in some sense, if you want to understand why the citation is about finding a super massive compact object rather than explicitly a black hole, I think understanding how close we are to this Schwarzschild radius is quite important. All right, so in astrophysics, there are two kinds of black holes that people talk about. And I think those two kinds are wonderful demonstrations of the different modes in which science works. So the first kinds of black holes that were thought of from a theoretical point of view were the stellar mass black holes. So people, and you're going to hear a lovely talk from Roger Penrose about this, thinking about the ultimate evolution of what would happen with a very massive star at the end of its life. Those kinds of objects will become stellar mass black holes. So objects that start their life, stars that start their life with roughly more than 30 times the mass of the sun are thought to become stellar mass black holes. So that was thought of theoretically, and now there's beautiful observational results. So as you heard Professor Genzel refer to, the gravitational wave detectors have really demonstrated very, very, very clearly that these stellar mass black holes exist. So the question of supermassive black holes, the story is very different. The story comes from the observations rather than the theory. So the story starts with observations. So observations of galaxies, and in particular active galactic nuclei, AGN, this is a small subset of galaxies, shows a tremendous amount of energy emanating out of its core. So this is a beautiful example where you see these jets of emission. You can measure how fast that gas is moving out. So you can measure the kinetic energy. And that tells you that there has to be something powering this phenomena. So that led people to hypothesize that there had to be a very massive, supermassive central engine, so a supermassive black hole at the center of these galaxies. And at the core of these galaxies, one also sees energy or light emerging that looks unlike anything produced by stars or gas. So that was the observational kick that got this idea of supermassive black holes going. Now, active galactic nuclei are actually a small set of all galaxies in the universe. They're roughly only 10% of all galaxies. So it was a few years later that people started to think, well, maybe it's possible that not only these really energetic galaxies having or hosting supermassive black holes, but perhaps it was possible that all galaxies harbor supermassive black holes at their centers, and that in the cases of non-active galactic nuclei, or galaxies that don't have centers that are very active, that the black hole is simply not accreting matter. So the idea being that the active galactic nuclei are being fueled by the accretion of matter onto the black hole, and that in the remaining galaxies, there's just not much matter around these black holes so that they don't drive all this energetic phenomena. Now, this is a galaxy that would look like our own if we could get out and look back at it. Our galaxy is complete. Our home galaxy is the Milky Way. It's completely ordinary, garden variety, nothing special about us. Our sun lives about halfway out in one of these spiral arms. And if we could get, and how we view it, because we're inside this galaxy, which is a flattened disk-like structure, we see the plane. So if you go out during the summer in particular, on a dark night, and look up, you can see the plane of the galaxy, which is that band of light. So we're looking towards the center of the galaxy. And what we want to establish is the presence of a supermassive black hole. And the most direct way you can do that is to look at the influence of stars. The influence of the black hole. See, it's still morning here. The influence of black hole on these stars. Now, I alluded at the beginning that we started this project thinking that it was going to be a much shorter project than it turned out to be. And that's because the anticipation was just to look at the stars' velocities, so their speed. So not seeing the full orbits, but rather just the beginning of the orbit. So just little line segments. And the anticipation is if there's a black hole, well, actually, let me step back. The stars should be moving under the influence of gravity. So you're really back to the very basic concept in physics, which is the force is mass times acceleration. And through that, you can figure out that the closer you are to the black hole, the faster stars should be moving. So you can measure on average or statistically that the stars closer to the black hole should be moving faster than the stars further away. If there's
it might be working now, because let's hope.
Hi, Roger.
It doesn't work. It doesn't work. I understand. Okay. Yes.
Hey, Roger, would you mind muting yourself for just a little bit?
Oh, they must be hearing me because.
Okay. Okay. So we have the stars. We're looking statistically. And because the key to this experiment, if you recall to the first few slides, is to show that there's a lot of mass inside a small volume, and you'd like to get within the Schwarzschild radius. You want to be able to see the stars that are as close to the center of the galaxy as possible. So you want the highest resolution, your angular resolution, your ability to see detail. And the larger your telescope, the larger, the smaller the scale that you can see, the better your angular resolution is. So this is called the diffraction limit of a telescope, and it scales just as the observing wavelength divided by the diameter of your mirror. So the bigger your mirror, the smaller the scale that you can see. So you really want to use the largest telescope that you can possibly get your hands on. But the challenge for, and so this is really why I wanted to come to UCLA was at the time that I started my job, UCLA, the University of California and Caltech had just built the largest telescope in the world, the Keck telescopes. The mirror there is 10 meters across. So this is roughly the width of a tennis court. And I guess I should say just I had been a grad student at Caltech. So I had seen the development of this telescope as I was finishing up my PhD work. And I really understood that if you want to do this work, you really need to get access to the Keck telescope. So this next generation of telescopes was really a key part of creating the moment that would enable this work to be done. Now, as you've already heard from Reinhard Genzel, the challenge is for these big telescopes is the atmosphere. The atmosphere blurs our images of astronomical sources. So the other aspect of the technology development that was essential for enabling this project, which in a sense seems so straightforward, was getting the technology going. So there's been a huge development in the arena of technology over the last 25 years. So we started off with very simple techniques. Both groups did. For the first 10 years, we used a technique called speckle imaging. It was very straightforward from a hardware perspective. Most of the work was done in software. And then came along adaptive optics, which enabled us to do this in real time. And the advent of this technology was really benefited from the declassification of military technology. So military, of course, also cares about looking up and down. So when they declassified their technology in the early 90s, the astrophysical community made a huge step forward in terms of understanding how to make this technique work. Anyway, this little animation shows you for the center of the galaxy, how much adaptive optics improves your ability to see what's going on. This little box inside is focused on where we think the black hole is. Without this technology, either speckle imaging or adaptive optics, you just can't see the stars, never mind track their motion. I think I'm going to pause here just for the sake, because it's really important actually to understand why this seemed hard, or some of the challenges we faced early on. So here I am, I'm an assistant professor. I thought I had a really good idea. When I put in my first proposal, it was actually turned down because the time so telescope time gets allocated every 6 months. So you have to write a proposal that says, this is how you do the experiment. This is how much time I need. And you have to justify what you're doing. So this group of scientists, your fellow peers, decides whether or not this is a good idea or not. And so they decided that this was indeed not a good proposal because they didn't think the technology would work at Keck. Keck was the first large this scale class that was up, and it was a segmented telescope. So it got to a 10-meter scale by putting together little 36 hexagonal pieces. So there was concern that the segments weren't aligned well enough to get to this diffraction limit. They also believed that we wouldn't see stars and that we wouldn't see them move. Now, anybody who was paying attention to what was going on, okay, this is sort of my bias. I think if you were paying attention, it was so clear that this was going to work. The technology had actually been proven on other telescopes. Keck had always been designed to get to the diffraction limit. So I have to say it was one of those early moments where it was just surprising, but nonetheless, I have to say my favorite expression is every challenge is an opportunity. It forces you to go back and write a better proposal and convince the people who didn't believe in you that what you have got going is indeed a good idea. And I think that's so much a part of doing science is the ability to kind of handle these hiccups that always happen. They either happen because you haven't kind of poked in the right direction, or because there's an external, either because of you internally or because of the outside world. Anyway, that's my just philosophical comment on science. All right, so now we're going to look at what actually happened. Oh, sorry. Let's see what actually happened. Well, what actually happened is the technique did work. I love looking at this animation. And this is animation. This is just describing how the stars move. Things are trailed with a dashed line when you see it with an image, a solid line when you see it spectroscopically, which gives you the motion along the line of sight. The star of the show, so to speak, is this one here. We call it SgrA, and it's the most powerful star for telling us, or the measurements of the star are the ones that are most powerful, because it's the brightest star that has a full orbit measured, both spectroscopically and in imaging domains. So in other words, you have the full set of measurements for telling you what's going on. And in the early phases, you did this statistically. Later on, you could use the individual stars, and that's so much more powerful because you can say that the mass is confined to a much smaller region. So we've taken what was understood in the early days, in the late 80s, that there's roughly 4 million times the mass of the sun inside a very large region, a region that was so large you just couldn't come close to claiming that there was a black hole. And this has confined that mass to a volume that's 10 million times smaller. So in a sense, this experiment, along with the one that's been done by the parallel team, has increased the evidence for supermassive black holes by a factor of 10 million. So this is really what's brought the case for supermassive black holes from a possibility to a certainty. All right, so we now have the strongest evidence to date for the existence of supermassive black holes in our own galaxy, or in fact, any galaxy. And that's quite ironic because it was really the other galaxies, the active galactic nuclei, that made us think of this idea in the first place, or our community in the first place. Now, I just want to end with a few comments on what's next, because that's really what the prize is recognizing is, oh, actually, let me go back. It's the best evidence today, but you should ask how close we are to the Schwarzschild radius. I'm not going to tell you, I'm just going to leave you with that thought. All right, so there are a lot of new mysteries, including understanding whether there are a lot of things we don't understand today in terms of what our observations have revealed. And I think this is, as a scientist, this is some of the most interesting moments when your technology has evolved enough that it gives you such a fundamentally new view of the universe that it reveals the unexpected. This is when, for me, science gets really fun because, again, it's pointing you the path forward to where there's much more knowledge to be gained. So in our case, at the center of the galaxy, you see young stars where no young stars should exist. In fact, the existence of a supermassive black hole and the low gas densities, and we can talk more about this if you'd like, should prevent stars from being formed. So I call this the paradox of youth. There are other theories that say there should be lots of, so the young stars here are the aqua stars. There are other theories that say that There should be lots of old stars because old stars have a lot of time to migrate inwards through what's called dynamical friction to the center of the galaxy, and should migrate around the most massive object in the system. And the old stars are the orange things. And then one of my favorites are the magenta objects, which we didn't even think to make predictions for. These are objects where the objects themselves are being tidally torn apart as they go through closest approach. And there's all sorts of new ideas that have arisen because of all three observations. So it's driving a lot of different research. So in light of time, I'm just going to leave you with that teaser and then move on to what you've already heard about, but I want to comment again on. The other exciting avenue going forward is using these stars to test more thoroughly how gravity works near a supermassive black hole. And as you'll hear much more from Sir Roger Penrose, that there's that the prediction is that you should get this mixing of space and time near the supermassive black hole. So this picture flattens one dimension of space and uses it for time, being the up and down version. So this mixing gets stronger as you move towards the black hole. So we're interested in using SO2 in particular now, and there because again, it's the only star that has a complete orbit with imaging and spectroscopy. That's what's made it so powerful. So as you already heard from Professor Genzel, the two teams have been after the gravitational redshift, which describes how the photon travels from the star itself to the telescope. So in other words, there should be an extra shift in where you see the energy that you see the light due to the energy it has to lose in climbing out of the gravitational potential well. This is most readily observed at closest approach. You need the whole orbit to tell you the shape of the orbit. So the first time the object goes through closest approach after you have a complete orbit. Now this orbit has a period of 16 years. So this is this happened in 2018. So both groups got very energized in 2018, and the results have confirmed the expected signal of the gravitational redshift. The next signal that you're after is the precession of the periapse, which describes this rotation that you heard about. So precession from general relativity should force the orbit to go in a prograde direction. So you can think of this as higher acceleration at closest approach than you would expect under Newtonian gravity. But it's also important to recognize that it could rotate in the opposite direction. And that would happen if there's mass surrounding the black hole, so that you would see at furthest approach more mass than you would see at closest approach, which would cause this orbit to open up. Now, the whole thing gets much more, the strongest signal, I mean, the signal is emerging now, but it becomes strongest by the time you hit apoapse. So I'm just going to leave you with the thought that our group may not be seeing the exact same thing, but we're still holding back because there are a lot of ways in which one could go wrong with this second test. Okay, so how to move forward? Technology is the way. The projects that I'm pushing forward on are more advanced adaptive optics. So instead of using one laser, we use multiple lasers. So this is being designed and built now. And that's essential if you want to get to the next generation of telescopes. So there are 3 such telescopes being built around the world: 30-meter telescope, which is a UC Caltech, Canada, Japan, China, and India. I feel like I forgot one partner, so I apologize if I have. And then the GMT, which is the Giant Magellan Telescope, and then the European Extremely Large Telescope. So all these telescopes are underway, and you really need that more advanced adaptive optics to use these bigger telescopes, because the bigger your telescopes, the less effective a single laser is. So this is just my anticipation of what should happen. This is where we are today on the left. The middle is where the new technology with adaptive optics on today's telescopes, and then tomorrow. And here it's just important to remember, we're just seeing the tip of the iceberg. Okay, so let me end by saying there are a lot of people involved in this research, a lot of students, and these students go off to all sorts of interesting careers. And from the point of view of you guys in high school, it's important to recognize that you may get a PhD in astrophysics, but you may go on to all sorts of different fields, because the training that you get in this field in data analytics and imaging is really useful for both the, let's see, there's students who go off to the military, there are students who go off to the finance, and big data analytics are sort of the three other fields that a lot of my students have gone into, other than just continuing on in astronomy and astrophysics. So let me end with, if nothing else, I hope these experiments have convinced you that there's a supermassive black hole at the center of the galaxy, and that so much of the work has revealed what's unexpected. Which I think, to me, is one of the most exciting things about being a scientist, is to explore the unexpected. So thanks for your attention.
Thank you very much. Can continue. I see now, Professor Penrose, you have connected. Do you have a presentation also that you can give now?
Oh, now can you?
Okay, now it worked. Excellent.
Good. Okay.
Do you have a presentation that you want to share?
I think I shall just reminisce and talk like that.
Okay.
If that's all right with you.
Yeah.
I shall take you back, first of all. Can you hear me? Can you still hear me?
Yes, we hear you.
Oh, good. Okay. No, I have to take you back to, I think, 1964, when none of this technology was available. You couldn't see stars going around a little spot in the middle of our galaxy. People, in fact, there was a question about what happened when bodies collapsed in the theory of general relativity, which was Einstein's theory of gravity, introduced in 1915. General relativity, this was, which is theory of gravity, which was based on the principle of equivalence, which was well known to Galileo, that if you drop a big rock and a little rock, they will fall at the same speed. And if you imagine a little insect sitting on one of the rocks and looking at the other one, it will be as though there is no gravity at all. So gravity can be cancelled out by falling freely in the gravitational field. And to make a theory, which Einstein was able to do, in which you didn't think in terms of the force of gravity, which is what Newton was thinking in terms of, because you can cancel the force away by falling freely. And he had to produce this theory, and it took him along a very different route from what anybody else was thinking of, because you had to think that space and time, well, first of all, space and time together were one thing. That was actually not due to Einstein. Einstein was thinking in terms of transformations of when you move from one observer to another observer and that sort of thing. But it was a mathematician called Minkowski who discovered that you could formulate the special relativity Einstein. There's no gravity, but you're looking at how things move when they move near the speed of light and how things transform, instead of thinking of trains and all that sort of thing, which were people arguing for, and clocks and all of that. Minkowski's view was to think in terms of space-time. So you have three space dimensions and another dimension, which is time. And you have a geometry, which is a bit like Euclidean geometry, but the time comes in a different way. See, when you take the distance between 2 points in Euclidean geometry, you have to take the three coordinates and you sum the squares and you take the square root, that sort of thing. But the thing with Minkowski's geometry, that you have a minus sign. So the time comes in with a different sign from the space. So it's very like Euclidean geometry, but there's a little difference because of the sign change. Anyway, when Einstein first heard about this Minkowskian geometry, he didn't like it at all. It took him a long while before he realized this was the right way to look at it. So then when he was persuaded that you should look at space and time together as a space-time in one thing, then this was a much better way of thinking. And Einstein was able to incorporate this into his theory of general relativity, in which the space-time was now not flat like Euclidean geometry, but you imagine the geometry of space and time together were actually curved. And the amount of curvature is this thing called the Riemann curvature. And it splits into two parts. One part is what the matter density itself creates. and the other is the free gravity. It's a bit like with electromagnetism. In electromagnetism, this is the theory due to Maxwell, who was a great physicist in the 19th century. And he produced this theory in which you have something like the source, which is the charge or the magnetic charge or the magnetic dipole or something like that, and the field. And there were two different things. The field was the electromagnetic field, and it's lucky he had this theory because that's the only way I can communicate with you now. Previously, it was only known that you visible light, but now we have radio waves, X-rays, all sorts of other things, and they came about because of Maxwell's wonderful equations. But these equations fitted in with the special theory of relativity that Einstein and Minkowski had introduced. But then when you had curved space, you need to think of the gravitational field is one part of the curvature, and that's like the Maxwell field, that is the electromagnetic field or the light or radio waves, and the other was the charge, and that was the other part of the curvature. And when you split this into these two parts, you could understand the theory much better. The curvature which it describes the gravitational waves, it introduces a distortion. So it's like looking a lens which is it's not just a convex or a concave lens, but a lens which is in one direction convex and the opposite direction concave, and it introduces this distortion in what you see. So things get squashed and stretched. So this is what space does when you have free gravity. And the gravitational wave detectors, the LIGO detector, for example, it experiences these very slight distortions in space and time, which come from the radiation gravitational waves coming from distant black holes, which are falling into each other and producing these waves. That won the Nobel Prize a couple of years ago. I forget how many years ago it was, very recently, when it was discovered that signals just like black holes falling into each other were detected in this LIGO detector just through these distortions of space-time. Now, let me go back to 1964 when I was starting to think about, it was because of the quasars, which I think were being described in the first talk you heard. The people were very puzzled by these signals, which seemed to be coming from very, very distant objects, but they were emitting energy which is about 1,000 times that in an entire galaxy. And people began to worry whether these were some very concentrated objects, which we would now call black holes. The term black hole didn't exist at that time. In fact, many people didn't believe these things could exist. I think Einstein would have believed they couldn't exist. Let me try and explain the problem. See, the problem comes about in 1939. There was actually a paper written by Oppenheimer and Snyder. Oppenheimer was the same Oppenheimer who was in charge of the nuclear bomb activities, but this was something he was doing quite different from that. And this paper described the collapse of a dust cloud. But it's really artificial material, but you think of something which is like dust, which has no pressure. And this is not only does it have no pressure, but it's supposed to be collapsing in this spherically symmetrical region. So imagine a spherically symmetrical ball of dust, which is collapsing. Now you see, it's gravitating itself, so it will fall inwards. And as it falls inwards, since it has no pressure, there's nothing that will stop it, so you might think. And it gets smaller and smaller and smaller, and it simply aims at this central point. And in their solution, Einstein, Oppenheimer, and Snyder, they described this solution of the Einstein equations in which this dust collapsed down and down and down. And they found at the very center, you got what's called a singularity. Now, a singularity is where the densities and the curvatures and everything goes to infinity and everything goes haywire, and there is no way of extending your equations. And lots of people didn't believe that this was realistic because, first of all, why not pressure? There might be, if there was pressure, you might expect that would stop the collapse. It doesn't actually work, but never mind. People would imagine it would stop the collapse. The second point, which is more important, is that it very likely would be irregular in some way. So some parts would be more dense, other parts less dense. It wouldn't be spherically symmetrical, it'd be irregular. And as it falls inwards, the irregularities would increase, get very, very complicated and quite different from the solution that Oppenheimer and Snyder had put forward. So who knows what happens? And many people thought, well, it would swish around, do something very complicated, and simply come swirling out again. And I think that was a common view. It was confirmed to some extent by a work that was done by a couple of Russians, Lifshitz and Khalatnikov, and they had written a paper. This was shortly before the quasar observations. The Oppenheimer-Snyder paper was in 1939, sorry. The Lifshitz and Khalatnikov paper was more contemporary with the observation of the quasars. And their conclusion was that in a general situation, you would not get singularities. So the picture would be that you get this collapse and it would just swirl around, do something complicated and come swirling out again. So I think that was the view that people mainly held. It wasn't clear. And John Wheeler, who was, I was visiting Princeton earlier, a little bit earlier than this time, and he had been very interested in this collapse problem and wondered what happened in general. And so I was quite acquainted with the sort of thing. But when the quasars were being observed and people started worrying about, well, maybe there is something involved, very important, maybe collections of stars, maybe it wouldn't be a single star, it could be lots and lots of stars coming together, swirling around and coming out again, or what? Would there be something like this black hole picture that was actually in the Oppenheimer-Snyder very specialized, very symmetrical model? So I started thinking about these problems, and I had various techniques that I'd been using basically the ideas of how light rays behave, how they focus, how they twist around, how regions would behave in general relativity. If you have a region and what are the light, all the signals which come out of some body, what kind of a boundary would that region be? And it would be generated by these light rays, but they would cross over and they would form caustics and crossing regions, and it would be very complicated to understand what happened. But I'd been working on this kind of thing for quite different reasons. And I got a feel how these boundaries of futures, if you like, behaved. And so I could pretty well understand what the boundaries looked like and how they were generated by these light rays. It's sort of a mathematical exercise, which I didn't know if it would really be useful to anybody. But then I started thinking about this collapse problem. And if it was not symmetrical, what could you do with it? Well, you see, two things that people at that time, if they were working in general relativity, there were two things they might do. One was work out exact solutions. We heard just the last talk about the Kerr solution, which actually represents a rotating black hole, but it wasn't very clear how general that would be. This was an example of people working on exact solutions. To work on exact solutions, you really had to simplify and have symmetries of one kind or another, and they wouldn't really apply to a general complicated collapse. So exact solutions wouldn't be much use for that. The other things people might do would be work on computer programs, and that's what people would do now. The computer the general relativity was put on computers, but not to an extent that you could actually solve this kind of a problem. And in any case, you wouldn't still know whether you get a singularity, because the singularity is a place where the curvatures and the densities go to infinity, and your computer program would just give up at that point. And you wouldn't know whether it's given up because it's really gone to infinity or simply because it got out of the range of the computer. So that wouldn't have been much help either. But I was working on these general sort of topological methods using how light rays behaves and so on. And I started thinking about this problem. And I remember walking in the woods at one time and wondering about what it would be like to fall into one of these regions that Oppenheimer and Snyder had considered, which we now call a collapse to a black hole, but the symmetrical case. And I began to think of, suppose things started to the curvatures get very big, would they run away and get bigger, or would they bounce away again? And it seemed to me that there is no way if you just looked at local arguments to see that it wouldn't just bounce away again. So it needed some non-local consideration. And so I was pondering about this and what kind of non-local characterization could you have for a collapse which had reached a point of no return. And I remember walking with a colleague. There was a colleague, I was walking towards my job. I had a job, I was a lecturer in London, and I was walking towards Birkbeck College where I worked. And my colleague who was talking to me at the time was Ivor Robinson. He was an Englishman who'd worked on exact solutions a lot of general relativity. He actually had a job in Dallas, Texas at the time, but he was visiting England and he was talking to me. He was a wonderful speaker. He could create wonderful images by his words. He was a very entertaining speaker. And he was talking to me and I was listening to him. And then we came to this side road where we had to cross the road. And in crossing the road, the conversation stopped. And then we got to the other side and he started talking to me. And then he went off and went home. And I remember having this strange feeling of elation. And I couldn't think why I was feeling elated. So I went through all the things that had happened during the day, what I'd had for breakfast and when I'd gone for my walk in the woods, that I'd gone on the tube train and come to my college and all that stuff. And nothing seemed to click. And then I remembered crossing the road and the idea came back to me, what I had at the time, which is an idea of what I called a trapped surface. Now, a trapped surface is a surface like it's closed up and it's spherical in nature. Imagine like a balloon, but it can be irregular. It doesn't have to be spherical. It can have bumps and wiggles, but it's generally smooth, but not spherical. Now, suppose you imagine a flash of light on that balloon, instantly all over the balloon. Now, suppose you imagine a place where the balloon is convex, then the light rays will diverge. But on the concave side, they'll converge. Wherever if it's concave, then it'll be the other way around. If it's saddle shaped in a place, whether they'll slightly converge and in both directions and slightly diverge. But the thing about a trapped surface is that the general tendency is converging both ways. That is to say, the flash of light going inwards from the balloon surface is converging. That's pretty obvious. The flash of light on the outside is also converging. So this is a very peculiar property which can happen just inside what's called the horizon. And this, we didn't have the idea of a horizon then, but just inside this region, which in the Oppenheimer-Snyder collapse would be this Schwarzschild radius. But if you're inside that, you find these surfaces, which I call trapped, where the light rays are converging in both ways. Now, it's hard to visualize this in a way, but if you just have a little piece of this surface, there's nothing wrong with it. You can have a trapped surface region in ordinary space and time, which doesn't mean anything. But if it's closed up, then you're in trouble. And I knew from the work I'd done before, I'm looking at the boundaries of futures. That is to imagine what is the future of this boundary region, what particle trajectories and what information, what kind of region can that spread out into? What's the boundary of it like? And I realized because of this trapped condition that it had to be what's called compact. And then I realized this was a contradiction. So that as long as the converging light rays couldn't sort of bend around and come out again, which they can't do unless you have negative energy. So as long as the energy is never negative, that is the local energy is never negative, and ordinary physics doesn't allow it to be negative, then you will have to have a contradiction. That is to say that the equations just give up at a certain point. And that was the theorem I had. Well, when I say give up, it means it's a singularity. So what I showed was that if you had a trapped surface and if the energies were never negative, then you had to have a singularity. Now, I'm not sure what people thought at the time. I remember Bob Dicke, who was a very distinguished experimental physicist, he was rather hoping that Einstein's general relativity was wrong because he had his own theory. And I remember I was talking about this in Princeton. He slapped me on the back and said, "Oh, you've done it, you see," because he thought I disproved general relativity. I think this was a reaction that a lot of people had. I didn't think it showed that. I think it showed that you really did have these singularities. But this probably meant that the curvatures get so big that somehow general relativity, the classical Einstein theory, does not work anymore, and you had to have a quantized version or something. I presume that was probably what went wrong. When you got these enormously large curvatures, that quantum mechanics comes in and maybe saves the day or does something, who knows? Still nobody knows, I should say. But anyway, that was the conclusion. What it tells you is that you can't have a collapse which reaches this point of no return, swishes round and comes swirling out again. It's got to produce a singularity. It might be that it produced a singularity which you could see. That's even worse than a black hole. The general feeling was that it had to be a black hole. And that was the conclusion that was deduced from this theorem that I had, which I published in. I gave a lecture in King's College, London. This was close to where I worked, actually. Well, not King's College, it wasn't quite as close as where I got my degree, which is University College in London, my undergraduate degree. But King's College was where I was giving this talk. And I gave a talk on this collapse theorem. In the movie, here we go. In the movie about Stephen Hawking, there's somebody who's supposed to be me giving a talk, and there's somebody supposed to be Stephen Hawking in the audience with sparks coming out of his head because he's being inspired by this torture, I should say, by this lecture. He wasn't there. I did give a talk, but Stephen Hawking was not present. There was a distinguished Irish physicist whose work I liked very much because he had a geometrical way of looking at general relativity, which I got a lot from. And J.L. Singh, and he was the talk, and he was interested. But a colleague of mine in Cambridge was very interested. This was Dennis Sharma, and he asked me to give a repeat talk in Cambridge. So I did give a repeat talk, and Stephen Hawking was at that talk, and then I had a private talk with him, and I think George Ellis, and described the techniques that I was using, and he picked up on them very quickly and generalized them to describe the other direction in time, that is to say, the Big Bang. You see, one place where you get singularities in this collapse, and the other place is that you go back in time and you encounter the Big Bang. So the same theorems would apply to the Big Bang as to the collapse. And Stephen produced various generalizations of my arguments mainly for the Big Bang, to show that was generic as well. And then we got together and wrote a paper jointly, which encompassed most of what we did before. And then I started thinking about, well, we've got these theorems, and they tell you all the complicated things that can happen with collapses. And it's not a simple thing like the Oppenheimer-Snyder model, which is very symmetrical. It can be very complicated, but you still always get these singularities in the future with collapse situations. And I remember thinking, okay, why don't you get all the complicated ones in the past? And I remember I was in Princeton at this time and going to a conference which was in Hoboken, New Jersey, which was where they used to have conferences quite regularly on relativity. And we had to drive up from Princeton to Hoboken. And I remember one of the cars, I was about to look whether that car could take me, and it was full up. And I saw in the middle of the car at the back was Jim Peebles, who was the Nobel Prize winner last year in physics. This was a long time before that, though. And I saw Jim Peebles at the back of the car. And I asked him this question. I said, but but there are many different models you can have of singularities. And the Big Bang is a very special one. Why don't you consider all these other models? And he looked at me and he said, because the universe is not like that. And I thought, gosh, it's not, is it? You see, this was a big revelation to me because it tells us that the Big Bang is really very, very different. Even though all these different solutions, you can have collapses, singularities, you can have different Big Bangs. Why don't we have all those different possible Big Bangs? Why this very special one? So I began to worry about why it's so different. You know, the physics in the future is the same as the physics in the past. So why do we have such a different situation? And initially I began just, I postulated. I remember saying, well, maybe there is a postulate that the Weyl curvature, that's the conformal curvature, which is the curvature of free gravity, why does that have to be 0 at the beginning? So I don't know why it's 0. Let's just postulate it. So I postulated the thing called the Weyl curvature hypothesis. And I thought that some very crazy kind of quantum gravity might produce this. Now you have to see that there's some very important reason why the initial Big Bang is so different from the singularities in the future. And this comes from a very, very fundamental principle of physics, which is called the second law of thermodynamics. The one thing which hasn't come up yet is the fact that in black holes, you have objects which have an absolutely enormous entropy. This is the Bekenstein-Hawking entropy of a black hole, which completely swamps any other entropy you have in the universe. People ask why black holes are important. One reason they're important is that they contain almost the entire entropy in the universe today. The second law of thermodynamics tells us that entropy increases with time. Entropy, which is a measure essentially of the randomness of things, this randomness is increasing with time. Black holes are very fortunate they're there because they sort of suck up the randomness and they allow the entropy of other things not to be as high because it's gone into the black holes. Now, in the very early universe, we didn't have black holes, or the time reverse of black holes, which people call white holes. They just weren't there. And it's a postulate they weren't there. And I thought that, well, since you've got to explain the singularities by combining quantum mechanics and general relativity, that's quantum gravity, there's got to be a very, very peculiar theory, which is time asymmetrical. And that's what I thought for a long time. But then, in order to characterize this initial state, one of my former students, that's Paul Todd, had a much better way of phrasing the initial state, which is that the Big Bang was of this particular character that you could stretch it out and it would disappear. That is to say, the singularity would disappear. You'd have a nice smooth singularity. Now, to explain this, I think I perhaps should have shown a picture. Maybe some of you will know these pictures by the Dutch artist M.C. Escher, and he produced a series of what he calls circle limits. The most famous one, as I think, with angels and devils interlocking. And you can see them getting smaller and smaller as they get to the edge, and the edge is this circular boundary to this region. Now, this is a representation of what's called hyperbolic geometry. It's a slight generalization of Euclidean geometry, but never mind about that. In this geometry, its infinity can be represented in this conformal way. Well, what do I mean by conformal? Conformal is a kind of geometry where you're interested in angles, but not distances. So you can imagine a triangle and a little triangle or a big triangle. If they're similar, conformally, they're identical. They might actually have circular curved boundaries or something. So, but the point is about conformal is that angles are preserved. Now, in relativity, it's very useful to think of conformal geometry. Conformal geometry is the geometry in which the light cones are preserved. So the light rays in the geometry are preserved, but the distances are not. And I mentioned Maxwell's famous equations of electromagnetism. These equations are completely insensitive to the distances. They are what's called conformally invariant. You can stretch or squash, and the Maxwell equations don't even notice it. I used to be playing around with this a lot because it was a very useful way of thinking about gravitational radiation. And you could make infinity finite, and then you can, instead of talking about limits, which I have lots of problems arguing about limits and things like that, but I like thinking about geometry. So what you think of is what the waves do when they actually get to infinity. And like in the Escher picture, you could draw infinity. Infinity is just like anywhere else. If there is no cosmological constant, now what's the cosmological constant? This was introduced by Einstein, I think it was in 1917, a couple of years after he'd introduced his initial theory, which was a term he put in for the wrong reason. He wanted the universe to be static and not expanding. But this was quickly shown to be wrong. The universe was expanding. So Einstein then retracted his cosmological constant. It was a double mistake. because he thought it was his greatest mistake. And so he retracted it, but it was actually right all along. So it was wrong to retract it. And this is what people call the exponential expansion or dark energy, which in the early days of this century have been observed by looking at distant supernovae. And you see that Einstein was actually right to introduce this cosmological constant and wrong to retract it.
Professor Penrose, I don't want to interrupt you, but we have to leave also some space for the students to ask.
Okay, so let me wrap up then. Can I wrap up?
Yes.
Okay, you see, what you do is you stretch out the Big Bang and then it becomes nice and smooth. And you squash infinity and it becomes nice and smooth. And so the Big Bang is not any old Big Bang, it's the conformal continuation of the remote future of a previous eon, as I'm calling it. And the previous eon signals, we have now a lot of evidence that this is true. I'm going to have a lot of trouble persuading people because people like to think of the Big Bang as the beginning of the universe. But in this model, which we, with various colleagues, we seem to see a lot of evidence that there was an eon prior to our Big Bang. And if people want me to ask, me questions about this, I'm quite happy to answer them. Thank you.
Okay, thank you very much. And now we go over to Q&A from Nacka Gymnasium. So who would like to start? Maybe you also know which one of the laureates you want to address the question to. Don't know it, I can try to direct it to the right person. Please start.
Well, all right. So Professor Ghez, and that goes to the same for Genzel, talks a lot about the development of technology during all of this research. And the development has been, well, apparently key to discovering these discoveries. So we just like to ask a question about how, in the future, Professor Ghez obviously talked about the adding more lasers to the telescopes. But if you're allowed to think freely, to continue and to get closer to this Rothschild radius, what advancement in technology would you like to see? What would enable something further in your field?
Was that directed to me? I'm sorry, I was a little confused.
I guess it's sort of, yeah, sure.
Okay. What it sounds like you'd like Genzel to respond. So Reinhard, you go ahead. There's all sorts of technology that's interesting. I mean, one would really like to discover stars that are closer in. And so here, what you've heard from the two talks are there are two different approaches. One is using a full aperture, like getting to a larger aperture, which is the 30-meter telescope approach, so you can get further in. And then the interferometer is also an important approach. And here there's an interesting tension between resolution and dynamic range. So you can think of a telescope as effectively an interferometer. And from the point of view of this adaptive optics business, you want to think of it as little apertures composed of the apertures being the scale length of the atmosphere, which at 2 microns is about, the number I carry around is 10 centimeters at optical wavelength. And then it gets bigger as roughly lambda to the 1.2. So it gets bigger at larger wavelengths. Anyway, you can think of it as a bunch of apertures around your big telescope. So that helps you contrast with the concept of an interferometer, where you have apertures that are further separated, so it gets you to higher angular resolution, but because it's not filled aperture, it reduces your dynamic range. So there's an interesting, the way to think about it really is there's opportunity in both dimensions. I mean, Reinhard can talk much more about the work with gravity, because I think this is a beautiful way of getting to higher resolution. But the challenge there is that there's much lower dynamic range. So the 30-meter telescope doesn't get you to quite the same resolution, because the diameter of the telescope isn't the baseline, but then you get much higher dynamic range. And it's a really crowded region. So I think both techniques will yield something interesting. Now, you also said freedom of thought, like don't constrain yourself. So if you want to talk about like, how are we going to learn about supermassive black holes more generally, this is such an exciting moment for astrophysics, because there's so many different technologies that are opening up our understanding of supermassive black holes. So for instance, the Event Horizon Telescope, which is detecting radio wavelengths, you're probing the gas, sees much closer to the event horizon. And then what's happening with LISA. So it's a space-based mission for gravitational waves. So it's an exciting moment from a technical point of view.
More questions?
Yes, I'm not quite sure who should answer this question, but I guess maybe Professor Ghez or Professor Genzel. And I wonder what usage the society has of black holes, and if there's any way to, if there's anything about black holes that you can apply on the everyday life.
Not really. But that's, I hope you will agree, that's actually not the point. The point is that these objects, by being so fascinating, not only fascinate the experts, us, but perhaps also you, because it's just a fantastic thing what the universe has done. See, the universe didn't have, I mean, I don't know whether the universe studied general relativity. I mean, it didn't have to produce massive black holes, was written nowhere, and we are not sure what kind of other species of black holes might actually exist, right? I mean, so-called intermediate mass black holes, which have a totally different way, probably. And so in that sense, it's a fascination. I always say, I walk through a forest, and with great surprise, I see there are blue flowers and red flowers. And that's sort of the first phase. And the next phase is you discover that the blue flowers are always on the left side of the path. Why is that? And that leads you to the physics part, so to speak. And you try to understand what the rules are and so forth. So it's just exploring the universe is, as Andrea already said, something which is just so fascinating.
Thank you.
I also have a question, and I guess this is more to Professor Penrose. If it's known that black holes consume energy from the universe, is it possible that there is an opposite phenomenon that spits out energy to compensate for everything that the black holes take? And also, is there a limit to how much energy a black hole can consume?
Well, the answer to the first question is, can you hear me?
Yes. Yep.
The question is that I once gave a talk on what was called black holes and white holes. And I wasn't quite sure what they meant by a black hole and white hole. I was given the title, but I assumed that probably what they meant was what you're saying, the time reverse of a black hole. Well, you see, in general relativity, there's nothing about the direction of time in the equations. So if you can have a black hole, which time is going one way, there's a perfectly good solution of the equations in which the time goes the other way. But the reason that we don't seem to see these in the universe has tied up with this whole question, which I was trying to express at the end of my talk, namely the connection with the second law of thermodynamics, which was absolutely fundamental to physics. The fact that you don't have black holes and the opposite of black holes, that is white holes, where the energy spews out instead of falling in, or matter gets spewed out. That was what a white hole should be. They just don't occur in physics because they would require an initial singularity of a kind that we don't have. Now, why don't we have that? Well, theoretically, according to Einstein's equations, we perfectly well could have. But there's something about the way the physics of the universe operates, which tells us that the initial state was free of gravitational degrees of freedom. In other words, you didn't have any white holes. But it's a very curious story because there's a subject in current cosmology called inflationary cosmology, this is supposed to represent a very, very early stage of the universe in which expansion took place at some ridiculously great rate in the first tiny 1 to the 10 to the minus 32 seconds or something like that, some ridiculously small fraction of a second, which is part of current cosmology. So if you read a book on current cosmology, you will see that this kind of inflationary phase was taking place, which is a bit like a white hole in a certain sense. Now, I never believed in it because it didn't really explain why the entropy was so low at the beginning and why you didn't have the kind of curvature that would produce a white hole or an initial state which had this kind of curvature that you can only get in black holes. It's a fact of the world that we don't see it, which is all tied up with this really fundamental law of physics called the second law of thermodynamics, which is why we exist at all. It has to do why the sun, you see, people used to say the sun gives us energy. It doesn't, because the energy from the sun goes out again at night, you see. If we got energy from the sun, it would heat the Earth up. What we get is energy in a low entropy form. That is to say, the sun is a hot spot in the dark sky. Well, let me not go into all that. But the fact is that gravitation, when you clump, the potential to clump is what we have in this universe, which means that the Big Bang, there was none of this. It was very, very uniform. You didn't have the clumpiness, and it was the potential to clump into stars and finally black holes, which is where the entropy is going all the time. And it's a fundamental to the picture, the whole way in which we think of the universe. We certainly don't understand why the Big Bang had to be of this nature. I have this model of my own, which tells you that it comes about because it was the continuation of the remote future of a previous eon, as I say. And that has to be stretched out until we get rid of all this gravitation. I can't go into all that now because it's complicated, confusing theory, I agree. But I just want to say that, yes, it's a very good question. The fact that you don't seem to have these white holes is absolutely fundamental.
Thank you. I think we have now had 3 questions from the students. There must be one student who has not posed a question yet.
No.
Yes.
Yeah, sure. I'll just take another then. Well, yeah, I had this. There's a lot of talk about black holes in time and space-time, and to non-scientists, that is very hard to grasp. But we do see a lot of that in science fiction films. A lot of time travel related stuff, concerning black holes. So it's really just a question of, do you think that, time travel might seem unlikely, but the key to discovering something close to time travel are the black holes and is found inside those black holes? Is there any truth to what we see in those films, or potential truth at least?
Well, the short answer to that is no.
Yes, Professor Penrose.
Sorry, the short answer to that question is no, there isn't any truth in it. It's certainly true that time is not as simple as we think. And the progression of time is affected by the motion. And in black holes, you have a very curious situation in which, certainly in the pictures one tends to draw, you tip the light cones over, which tells you it looks as though time is progressing towards the center. But you should really draw the picture in a different way. Time doesn't go sideways. It's always going in a time-like direction, if that makes any sense. But the thing is, it heads for the singularity. So if you fell into a black hole, your direction of time would be to head for that singularity, and there's no escape. It doesn't really help. You see, black holes, you might think, were wonderful things for science fiction stories, but they're a bit disappointing on the whole, because you have to change the rules, because once you've fallen in it, there's nothing you can do about it. There's no escape. It might be quite interesting to do things where you haven't fallen into it, and you can do. I think that in the movie there was something where people took advantage of the. You can, if you haven't quite fallen into it, you can escape by throwing something else into the black hole with a certain velocity, and you might get away. But that's not through the horizon. That's only through what's called the
I mean, if I may say on time travel, not with respect to black holes, but time travel. I travel time all the time as an astronomer. I can do that in reality, and because of the finite speed of light, okay? So we can look back in time, look at objects which, as they were, a long time ago, including very close to the Big Bang. And that's real, okay? I mean, so it's a very normal thing to do.
Actually, let me also poke at the beginning, which where I think the statement was made that it seemed all this mixing of space-time seems so abstract and far removed. But in fact, if any of you, which I mean, most of us use our cell phones to get around, from point A to point B, you cannot do that without your phone intrinsically taking advantage of general relativity. In other words, our ability to find our position so precisely on Earth depends on these GPS systems, these satellites that are looking at the GR effects from the Earth. So it's actually something we don't realize that we're really taking advantage of all the time.
That's right, but you're not looking at you're not looking at travel. Yes,
absolutely. So I'm just trying to make the point that while we think of a lot of this, the stuff that we're talking about is abstract, there are aspects of this that are pulled in. But as Roger,
I completely agree that general relativity is becoming extremely important, and I think it's important in another way, which people. When it combines with quantum mechanics, and people talk about quantum gravity, you see, that's where curvatures get enormously large. There's the opposite of quantum gravity, which is what I call gravitational quantum mechanics, or the gravitizing quantum mechanics, and that will be very important. It has to do with, in my view, with the collapse of the wave function, which is something we have absolutely no theory of at the moment. But in my view, it's when we try to bring gravity and quantum mechanics together, we're going to revolutionize how we use quantum mechanics. That's for the future.
Oh, for sure, yes. More questions?
Yes, I have a question, which is a quite general question about researching. And I guess it's a quite interesting question to all students who might struggle to find motivation sometimes. And obviously you have dedicated a large amount of time and effort to your research. And I wonder if you have met a lot of criticism by other scientists who has not believed in this project during the years. And if so, how you have handled to keep going and eventually reach the goal.
Certainly, criticism. Well, I think certainly in the early days, when I was worrying about the singularities and trying to show that they were generic in general relativity, that put a lot of people off general relativity. As I mentioned, Bob Dicke, there was a very well-known physicist, an important physicist called Philip Morrison. And he didn't believe in black holes, and I eventually got it out of him. He didn't believe in general relativity. So it took a long time before this amazing theory, which was 1915, when was it? I keep forgetting. When Einstein introduced the theory, well, he was playing around with it a lot time earlier than that. And very few people took it seriously. And it wasn't really part of physics in a serious way until I think the quasars came along. And then there was a big conference in Dallas, Texas. It was the first of the quantum, what are they called? I can't remember the name of the conferences now. Well, they were called Texas conferences on relativity or something. But anyway, these conferences started then, and they started to show the importance of bringing general relativity even into cosmology. So now, as Andrea was just mentioning a minute ago, they are, just even driving around and finding where you are on the Earth because of having the satellites and the extraordinary precision we now have in measurements, and the fact that you can tell where you are by the signals coming from satellites and reflected from satellites. And you have to bring in general relativity or get the wrong answer. by quite a long way. I think I can't remember the answer to that, but you certainly get the wrong answer without general relativity. So it's there. It's part of physics, and it's a huge challenge to see how this theory. Well, we're beginning to see how to make use of it in various ways. It's a huge challenge to see how it's going to fit in properly with quantum mechanics. And I think the challenge is not what many people think, finding a quantum theory of gravity, but to try to understand how gravity influences the real big problem of quantum mechanics. Quantum mechanics has this fundamental problem, which is what's called the measurement problem, or the problem of how you do two different things in quantum mechanics. One is you have this wonderful equation called the Schrodinger equation, which tells you how the state of the system evolves with time. It evolves and it evolves, and then suddenly you throw it in the waste paper basket. This was Schrodinger pointing this out himself by describing his cat. You see, the Schrodinger's cat is really basically Schrodinger showing the ridiculous implications of his own equation. Some people say, oh, well, you could make a Schrodinger's cat, which was dead and alive at the same time. Schrodinger was really saying, no, this is absurd. We've got to find out what it is that makes the universe measure itself in a certain sense from time to time, deviate from the Schrodinger equation, jump from one thing to another. And in my view, this is bringing general relativity into the quantum mechanics picture. And there's a huge challenge for people to find the right theory, the right experiments. There are some experiments already. Nobody has concluded them as yet. There was one by Dirk Baumeister, which has been going on for several decades. And I think he's getting very close to seeing whether this gravitational effect is actually going to have an influence on quantum mechanics. We'll have to see. But I think that's a major challenge for physics in the not so distant future. Have a good theory and good experiments which can test these theories.
So there you see, you have challenges now for the future for the student panel. I think we are now almost half hour over time. So it's time now to wrap up. Thank you for the questions. Do you have some final words? For the Nobel Laureate I'm addressing now, do you have some final words for the students?
Go for it.
Do what you feel you like. You see, people often told me to go into different areas, but I just did what I like doing. I think that's an important challenge. Of course, it may be completely off the wall, in which case, yes, you should be turned back and do something more sensible. But on the other hand, if there's a choice between doing something you like and something you feel you ought to do, on the whole, I would say do what you like.
Professor Genzel, do you have some final words also? Or?
I much agree with this. This makes life interesting. And look at Roger, he's as young as he could be. It's wonderful to see. And, research keeps you young.
I hope so. I keep going. I hope so. Yeah.
Thank you very much, all of you, for participating. And I hand now over the word to Peter, who is still here, I hope.
Yes, no, we will hand give the word to Helen.
Okay.
Dear Nobel Laureates, Academy member and students of Nacka Gymnasium, thank you all for your generous and engaging contributions to this meeting. And a special thank you to Professor Penrose, Professor Genzel, and Professor Ghez for sharing your time, thoughts, and knowledge with us. Thank you.
Our pleasure.
Yeah, thank you for your questions.
Thank you.
Thank you.
Thank you.